Okay, there we go. All right, so first let me begin by saying that I'm very grateful to the organizers for giving me this opportunity to be here to honor Pascal, who's been a tremendous collaborator for me and also a great friend for many years. In fact, I think probably, as I look around the room, it may be that I collaborated with Pascal earlier, further back in the past than anybody else in the room, I suspect. I'm not sure.
Anybody else need it?
2 years ago. You're not that old.
And yeah. Anyway, it's been a great pleasure because Pascal is both a wonderful mathematician and a great friend. And if I'm allowed to say so, I think our collaboration was pretty successful. For sure, we proved at least one good result. And speaking of that one good result, this is a good time to remember Ellen McIntosh, who was also a great friend to both of us and a great collaborator. And I think both Pascal would agree with me that he was the one that was kind of responsible for getting us both involved in working on the problem that led to that one good result. So we'll drink a toast to Ellen tonight. Okay, but now to business. You'll notice that I've preloaded some information on the board to save time. So let me explain a little bit about that. About 5 weeks ago, I gave a version of this talk at a conference at the University of Arkansas, just to practice. And then the last couple of nights, as we were sitting outside enjoying the nice evening and drinking a little grappa, we had a visitation of wild pigs. This is going somewhere. The wild pigs reminded me of Arkansas, where the university's football team has a mascot, which is a wild pig. So being reminded of Arkansas, I remember that when I gave this talk, I was not able to get quite as far and cover quite as much material as I'd hoped to do. So therefore, I've tried to expedite matters by preloading some material on the board. So let me just review this quickly. Omega is going to be an open set in Rn plus 1, which in the parabolic setting, which is mainly what I'm focusing on, will be space-time, n space dimensions and one time dimension. Sigma is going to be the boundary of omega, capital sigma. Lowercase sigma is going to be surface measure. In the elliptic case, that's just standard Hn measure restricted to sigma. In the parabolic case, it's parabolic Hn plus 1 measure restricted to sigma. Parabolic Hausdorff measure is defined just like normal Hausdorff measure, except that you measure the diameters of your sets in the parabolic metric, which is basically this right here. The distance between xt and ys is this little bit right here, x minus y plus t minus s to the 1/2. And n plus 1 is the right dimension because in n plus 1, in Rn plus 1, the parabolic homogeneous dimension is actually n plus 2, right? Because parabolic cubes have dimension r in the spatial variable and r squared in the time variable. Okay, so codimension 1, you would work with n plus 1 dimensional parabolic Hausdorff measure. AR stands for all fours regularity. It means that the sigma measure of a surface ball is either on the order of r to the n in the elliptic case or n plus 1 in the parabolic case. Delta r here means a surface ball or surface cube, the intersection with a Euclidean ball or Euclidean or parabolic Euclidean cube with the boundary. Uniform rectifiability is going to be an important concept for us. This is, of course, the tremendous theory developed by David and Sems. I'm going to take as a definition the one involving the betas. That beta squared d sigma of x dr over r is a Carlson measure. I've written the elliptic one here, but I'll explain in a moment about the parabolic one. Is a Carlson measure on sigma crossed with 0 infinity. And beta squared xr is defined, the square of it is defined this way. You take the average over delta r, take the distance from y to a hyperplane P, divide by r square that, integrate with respect to sigma, and then take the infimum over all hyperplanes P. The parabolic version is similar, only of course the center is at x and t. This surface ball or surface cube is a parabolic one. And we're taking the infimum over all hyperplanes that are parallel to the time axis, and that's natural. Okay, that's definitely the right thing to do. Okay, Lipschitz in the parabolic sense, and I'll just write lip when it's understood we're talking about parabolic. It means lip 1/1/2. Lipschitz in the space variable and lip 1/2 in time. Weak infinity means that you have a measure which I'll conveniently call omega, which is absolutely continuous with respect to sigma, and its density k satisfies this reverse Helder inequality. Q is, this is for some q bigger than 1, okay? And it's a weak infinity because we have to double the surface ball on the right-hand side, all right? If k is the Poisson kernel, it's well known and kind of heuristically easy to see that this is equivalent to solvability of the Dirichlet problem for p in the dual range, because if you're going to integrate against data belonging to LP, you're integrating against harmonic measure, then the density of harmonic measure better belong to the dual LP space, to the one where you're taking your data, right? Okay, and this makes it scale invariant and quantitative, okay? A infinity is just weak infinity plus doubling. And one last concept, the notion of a corkscrew point. You take a Euclidean ball center at the boundary of radius r, then inside the intersection of the ball with your domain, there's another ball of radius, let's say c times r for some uniform constant c. And of course the parabolic analog of that is the same. We use a parabolic ball or parabolic cylinder or parabolic cube, okay? All right, okay, and now to business here. So the setting is basically this. It's some of the motivation here is this sort of classical one-phase free boundary problem where we have an open set omega, which is the set where some solution u to a PDE, it could be a variational problem, but for me it's going to be a PDE, is positive, okay? And sigma is going to be the boundary, the free boundary. And of course, notice that the boundary of the set where u is positive, we're going to have u identically 0 here. All right? And then the fundamental question is, if we're given some info regarding the length of the gradient of u on sigma, which of course means we're just taking the inner normal derivative of u because the tangential derivatives vanish on this level set, okay? Then what can we say? Does this imply some kind of regularity of the free boundary sigma? And heuristically, it ought to do, philosophically it ought to do, because this is an overdetermined problem, right? We're specifying both Dirichlet data and Neumann information as well. And that's too much information unless you it imposes some constraints upon the boundary itself, okay? Just a comment here, which is that in the presence of what some people call the comparison principle, and what a lot of potential theory people call the boundary Harmonic principle, which is this fact that if you have two positive solutions vanishing on a surface ball continuously, then their ratio is bounded above and below in a uniform way as you go to the boundary, okay? In that case, then u might as well be a green function with some fixed pool where we're maybe kind of thinking of this as a local picture and the pole is away from where we're working, okay? And in that case, the UDN is K, the Poisson kernel. Poisson, the dotted I goes there. Okay? All right, so in this setting, well, maybe I should digress for a second. Some of the situations in which I'm going to work today, this will be valid, sometimes it's not, but in any case, from now on, we're going to be focusing on the Poisson kernel Or in the caloric case, where I'll still call it the Poisson kernel, it's still the density of the caloric measure in that case with respect to sigma. Okay? All right, so some previous work in this area. There's the fundamental result. To save myself time, I'm going to just use initial. So there's this fundamental work of Alt and Caffarelli. It's sort of a follow-up by Jerison. I'll explain what the results are in a second.
Steve, before I go on, can I ask you a stupid question?
Mm-hmm.
So the comparison principle is, of course, about solutions, not normal or any other derivatives. Is it the case that, I mean, I know what games you like with the Poisson kernel, so is it the case that you take any other solution and you take normal derivative of that other solution and you can deduce the same, I don't know, reverse Herder properties for normal derivative of that other solution?
Yeah, I think so. You can go through the comparison principle. Yeah.
So into reverse Herder, you can do always just by blind.
If you've got it for the Poisson kernel, you're going to have it for another U, that a positive solution U that vanishes, at least locally.
Locally,
Yeah, locally where it vanishes on the surface ball. Yeah. Okay. Combinatorial, again, I'll explain in a second. Lewis and Vogel, and then this is joint work with a former student Philly, Chima Martel, and Kai Nystrom. So what's this about? This result, okay, so in all of these, and basically everything I'm going to talk about today, we're always going to have this all-fours regularity assumption as a background hypothesis. So all of these results, that's a background hypothesis. For these two, there's an additional background hypothesis of Reifenberg flatness. Let's not worry too much about that, but it says that the boundary is pretty damn flat at all scales, or at least all scales below a certain scale, okay? And with, in addition, topological separation between omega and its complement, but let's not worry about that. Okay, and so what did these guys do? They showed that the log of the Poisson kernel is in C alpha for some alpha between 0 and 1, implies that sigma is C1 alpha, which, in other words, we're saying that the unit normal to the boundary is in C alpha, okay? Kennigan-Toro did an endpoint version of this where, same business, but we replace C alpha by VMO, okay, vanishing mean oscillation. All right, in fact, they showed both directions, and in fact, the converse to this is true as well. That's a classical result about 100 years ago due to Kellogg, who incidentally was also a professor at the University of Missouri, but then he got famous and he got a job at Harvard. Harvard has not offered me a job yet.
Let's give us a call.
So the work that Lewis and Vogel did was they showed that if K suitably normalized is like 1, of course this is normalized and localized, all right? Which in other words is saying that omega is like sigma, again, localized and normalized, all right? Then the boundary is uniformly rectifiable. Again, it satisfies this quantitative rectifiability condition that was developed by David and Sebs. Okay? And then this result is an extension of this. We show that if omega is weak A infinity with respect to sigma, again, in some appropriate scale invariant way, then again, sigma is uniformly rectifiable. Okay? Voilà. Maybe come back to me. One last comment before I send this up. Let me point out that this last result can be thought of as sort of a large constant version of the Kennigan-Toro result. Why do I say that? Well, because, okay, if instead of weak infinity, suppose we had A infinity, we don't, but suppose we have A infinity, okay? Well, k in A infinity, or omega in A infinity, however you want to say it, is almost like saying that the log of k is in BMO. Of course, it's not quite that, but it's not that far off, okay? All right, and on the other hand, this flatness that you get here from having Reifenberg flatness offers regularity and the unit normal in VMO tells you that you have uniform rectifiability with some kind of vanishing trace. So like the Carlson measure condition on the betas, as you shrink the scales down to zero, it'll be like a VMO-like condition. As they shrink the scales down to zero, the constants that you get shrink to zero. Okay? All right. Now let's send this guy out. Okay. What about the parabolic setting? Or parabolic for me today, this just means caloric. Okay? It can always be the heat operator. And let me go ahead and tell you what that is. It's that, as usual. So 2 results so far, both in these sort of small constant conditions, smooth conditions. All right, so there was a joint result with John Lewis and Kai Nystrom, where we showed a caloric version of the Canning-Toro result, except not quite the full thing. We had an extra hypothesis, okay? Okay. All right, and then Max Engelstein got the full thing. He got the full caloric KT plus caloric alt-Caffarelli and Jerison. Oh, by the way, why do I have this slash there as 2 separate results? Alt-Caffarelli's original result, the alphas aren't necessarily the same. They show that log K is in C alpha, then N is in C beta, or beta might be less than alpha, and Jerison showed you can take them to be the same alpha. Okay? All right, so the question that's going to occupy us today is what about the large constant version of this result, that where you have weak infinity? Does it give you the parabolic version of uniform rectifiability? Okay? All right, and so to provide a bit more context, let me give you a little more background. Okay, the first thing is that there's this classical result of Dahlberg from '77, famous thing for which he got the Salem Prize. He showed that if sigma is Lipschitz, or locally Lipschitz, so in other words, omega is a Lipschitz domain, then omega is an A infinity with respect to sigma. And in fact, he showed even more than that. He showed that in this reverse Elder condition, you could take Q equals 2, which gives you L2 solvability of the Dirichlet problem. Okay? So shortly after Dahlberg did that, then Hunt made the conjecture that the same, you should be able to prove a caloric version of Dahlberg's theorem for parabolic Lipschitz domains. For emphasis, the P means parabolic. Okay? So this lip 1/1/2 condition. That's false. Okay? And there's a counterexample due to Kaufman and Wu. All right? On the other hand, there was a fundamental breakthrough of Lewis and Murray. This is important enough for my purposes that I'm going to spell their names. In '93, I know. Dahlberg did get spelled as well. And Hunt. There's no consistency here. And what did these guys prove? They proved that if sigma is something that I'll abbreviate as R-lip, which stands for regular lip 1/1/2, and I'll tell you in a moment what that means, that implies that omega is A infinity with respect to sigma. Okay? By the way, In a lip 1/1/2 domain, caloric measure is always doubling. This is a result of Fab's, Garofalo, and Salsa. So you've got doubling in that case. So once you've got weak infinity, you've got fully infinity. Okay? All right. So our lip, I'm about to tell you. Yeah. Okay, come on. There we go. Okay. So what does our lip mean? So our lip, so that means this is the graph of a function that's our lip, and sigma of xt is our lip, means that it's Lipschitz in the usual sense in the space variable uniformly in T, and if we take dt composed with the negative square root of the heat operator on Rn, apply that to psi, that's going to be in parabolic BMO, meaning you take the BMO with respect to parabolic cubes. Okay? Remember, H is the heat operator. In this case, it's the heat operator in Rn. This, taking the negative square root of it, means that it's a parabolic fractional integral of parabolic order 1, which means it smooths by a full order in space and half an order in time. And then you compose this with a full time derivative, so the net effect of differentiation in time is a half order time derivative. Okay? All right? And this is related to the work of Strickart's, I spell him again, on BMO Sobolev spaces. So in particular, using Strickart's ideas, it's easy to see that this implies in particular that it's lip 1/2 in the time variable, but it's actually better in a subtle way. Okay? In fact, it has to be better because you get a infinity here, whereas this is false. In fact, the Kaufman and Wu example, the caloric measure fails to be absolutely continuous with respect to sigma. Okay? All right. Okay, so that's very nice. Maybe I should say a little bit more about our lip. Okay, so suppose we already know that psi is Lipschitz in X in the usual sense, okay, uniformly in T. Then psi is in our lip if and only if we have the following expression being a parabolic Carlson measure. If and only if, and I'll explain what I mean here in a second. If and only if this expression is a parabolic Carlson measure, which is like a usual Carlson measure on, let me emphasize, on 0 infinity cross Rn minus 1, spatial coordinates in X, and of course one time direction. Okay? So this is defined like a Carlson measure in the usual way, except the cubes are parabolic. Okay? And here PR is a nice parabolic approximate identity. And maybe, so I can refer back to it later, we'll call that star. Okay, the fact that this expression should be a Carlson measure. If it is, then your psi is our lip. Okay? All right. Nope. What do I want to do? I want to send that guy up. And bring this guy down. No, not wrong one. Yeah, technology is my bane. There we go. There we go. Okay. Okay, so this leads us up to the results I want to talk about today. All right, and this is joint work with Simon Borks. I'll spell my co-authors' names. Jimmo Martel, Kai Nystrom, and there are two theorems. Theorem 1 is the converse to the Lewis-Murray theorem, which is something that John Lewis and I had conjectured ought to be true back in the 90s, but now we finally know it's true. Okay? So this is converse of the Lewis-Murray result. Okay, so we suppose that psi is a parabolic Lipschitz graph, so lip 1, 1/2. And caloric measure is A infinity with respect to sigma. And then the conclusion is that in fact psi actually is R-lip. So the R-lip condition is, at least among parabolic graph domains, it's the necessary and sufficient condition for caloric measure to be A infinity with respect to sigma, and hence it characterizes solvability of the Dirichlet problem with data in some LP space with P finite, so for singular data in the LP scale. Okay? And then theorem 2, which is sort of the general case, we're going to suppose that omega satisfies the corkscrew condition, which remember I put on the board at the beginning. Okay, this will be, of course, in the parabolic sense, but that's fine. And we're going to assume that sigma, the boundary, by the way, if you're worried about the fact that in the parabolic setting you can have all these different parts of the boundary, for what we're doing, it's going to be the case that all the boundary is the lateral boundary. Okay? You can also do things where there's some kind of initial boundary, but this will minimize technicalities. Okay? All right? So this is going to be something that we call time-symmetric all-fours regular. I'll tell you in a second what that is. I apologize for the unfortunate acronym there. I'm not by any means endorsing Putinism here. And we're going to suppose that, of course, omega, and we're now in a setting where we don't necessarily have doubling anymore, so we're going to assume that it's in weak infinity with respect to sigma. And the conclusion is that then sigma is parabolic version of uniformly rectifiable. Okay? And now in this remaining time, which is, what do I have, Svetlana? About 23 minutes? Yeah, okay. All right. So let me give you sort of a brief sketch. I won't do this justice by any means. But let me try to give a brief sketch of at least some of the ideas involved in both of these proofs.
Were you already just R-lip and uniformly rectifiable?
Yeah, good question. Actually, it's a very good question. In fact, for a parabolic Lipschitz that is lip 1, 1/2 graph domain, uniform rectifiability of such a graph is equivalent to it being R-lip. Okay? So R-lip, for a lip 1, 1/2 graph, being uniformly rectifiable means it's R-lip and vice versa. Yeah.
But that's for a graph, right?
That's for the graphs. If you already know it's a graph, then to be uniformly rectifiable means that it's R-lip. That's equivalent. Yeah.
Okay.
Yeah. Thank you for asking that question, because I should have said that already. Okay, so sketches of the proofs. Okay, so let's talk about theorem 1 first. All right. So theorem 1, we want to verify that this guy is R-lip. So, you know, what you might think you'd try to do is verify this condition here, this Carlson condition that I called star. We're not going to do that. We're going to do a substitute for that. This is somehow the key idea. Where we're going to look at level sets of u, which is really we're thinking of as being some normalized green function, all right, with pole that's away from where we're working. Okay, so we're going to be looking at level sets of the green function, and a level set at height r is somehow going to substitute for PR of psi. Okay, so let me explain how this is going to go. So to my knowledge, this is, so looking at level sets of the green function, of course this is, or level sets of this function u, this is a normal thing to do in free boundary theory. But I think the thing that's new and different here is that we're going to do Littlewood Paley theory with this guy. We're going to prove these square function estimates. Okay. All right. So so notice that sigma itself, we can think of that as sigma 0. This is a level set where u equals 0. So then we'll, for r positive, sigma r is going to be the level set where u equals r. And for the moment, I'm going to claim that at least locally, sigma r is a graph of, say, let's call it psi r of xt. Okay? I'm going to claim that. All right? So let's take that claim for granted for a moment. And then the goal is to prove a substitute version of star with psi r of xt in place of PR of psi, which is this extension by a nice approximate identity. And it turns out, with some harmonic analysis, that that's still enough. One can show that this still implies that psi is R lit. Okay? All right, so that's the goal. All right, so first of all, let me explain this claim. Why is it a graph? Well, there's this result of Caffarelli and Salsa, which says that, okay, some notation. I'm going to think of if this is psi, if this is the graph of psi of xt, I'm going to think of x naught as being the transverse variable. So the graph is sigma equals the set of x naught xt, such that x naught is psi of xt. Okay? All right? And if we differentiate in this vertical variable, the Caffarelli-Salsa result says that at least locally, du dx naught is comparable to u over the distance to the boundary. Delta is the distance to the boundary, in this case, the parabolic distance. Okay? Of course, one direction, this direction is just standard interior estimates for the heat equation. The deep fact is the other direction. Okay? But it's true, these guys proved it. And notice what that says. This is, of course, a strictly positive quantity, which says that u is strictly increasing as you move upwards vertically, and so, of course, this is a graph. Okay? The level set has to be a graph then. All right? Okay, but then it turns out that a consequence of the A infinity property is that u over delta is like 1 in a uniform way once U has been suitably normalized, is like 1 a lot. That means in a sawtooth subdomain that locally has a very, very ample contact with the original boundary, okay? And of course that means that the same holds for this guy in a local way, okay? All right. But if that's the case, that means that we can use implicit differentiation to get some estimates for derivatives of psi r in terms of derivatives of u, okay? So, for example, if you look at the level set equation, and the simplest computation is when we differentiate in t, okay, both sides of the equation. This is going to be ux naught times dt of psi r plus ut, and that's going to equal 0. But this, we just said, a lot of time that's like 1, which means that a lot of time the absolute value of this guy and the absolute value of this guy is basically the same. And similar things hold for 2 spatial derivatives, okay? All right, and so what that means is that this substitute version of star, where we replace PR of psi by psi r, can be reduced to local square function bounds for spatial gradient. Here capital X is going to be x naught x of squared of u of xt squared plus dtu squared times distance to the boundary times dx dt. All right? And these in turn, okay, how do we prove that? Well, remember, delta is like u. So we get to put, at least a lot of the time, so we get to replace delta by u. And this should be xt. Okay? And then there's a very clever integration by parts argument that goes back to John Lewis and Kai Nystrom back, I don't know, this is maybe 17 years old now, sometime around this, 2007, maybe 2008. They prove an integration by parts argument that's a little subtle because in the elliptic case, in the harmonic case, it's just the classical integration by parts argument. But you would like to actually have an adjoint solution here. But they somehow managed to make it work without working with the adjoint, with this being the solution of the heat equation as well, the same u, okay? All right, and that does the trick, okay? And that's basically the sketch of the idea of theorem 1. Okay, so now in this remaining time, let me talk about theorem 2. Oh, I should have left it? I suppose I should have left it. Okay, so one thing I need to tell you about is what is, okay, I'll just remind you, all right. So we're assuming that we have interior corkscrews and that sigma is TS ADR, and I need to tell you what that is. Okay, and omega is going to be in VK infinity, and we want to show that this implies that sigma is PU1. Okay, so what is time symmetric? Oops. Guy is in the room. So that's why I have this unfortunate Russian acronym.
Actually looks better with the, you know.
I know, I don't like that word. We're stuck with it. Okay, so what does this mean? Okay, it means you have the upper all fours bound in the usual sense, but if we intersect the boundary with a parabolic cube or cylinder And for me, I know this is weird for a lot of parabolic people, but I'm gonna let the time axis run this way. Okay, I'm gonna let it run horizontally. Okay? So this is so if this is IR, this is IR plus, the time forward half, and this is IR minus, the time backwards half. The intersection with the boundary is delta R minus and delta R plus. And time symmetric all-fours regularity means that you get the lower all-fours regular bound for the sigma measure of each of these, only looking at the time forward half and only looking at the time backward half. Okay, and what does that do for you? Well, it gives you, the backwards one gives you ample thermal capacity. This one gives you adjoint thermal capacity. So it lets you have things like Hiller continuity at the boundary, both for solutions and adjoint solutions. Okay? All right. Okay. All right, so what are we gonna do now? Okay, so let me digress for just a second, which is to give you a philosophical idea, which goes back to Alt Caffarelli, but it's used by everyone subsequently, by Koenig and Toro, by Lewis and Vogel, by us. Okay, but it's really due to these guys, and the idea is that oscillation of the gradient of the green function being small implies some kind of flatness. And remember, uniform rectifiability is about flatness. Okay? Think of the betas. You're approximating by hyperplanes. Okay? So why is that? Well, that's easy enough to see. Oh, here, G is U. So let me, okay? All right? So why is that? Well, gradient of U being close to constant means that U is close to linear. And remember that on sigma, that's the zero set, and without loss of generality, we can translate so that the origin belongs to sigma, and since that's the zero set of U, therefore, U of 0 equals 0. And if it's linear, that means, therefore, U is like A dotted with X, where A is some constant vector, and of course the zero set of this guy is a hyperplane whose normal is A, okay? And notice that, of course, grad U is perpendicular, or roughly perpendicular to the plane that gives you, that's approximating the zero set, okay? All right. I don't need that anymore. Okay. Okay, so what's the flatness that we're going to deduce? Well, there's some initial flatness, which in the elliptic case is actually enough. And so there's some flatness that you get, it turns out, that, and this is what we did in the HLMN paper, but somehow using ideas from Lewis and Vogel. The flatness that we get is something that we call the weak half-space approximation property, and what it means is that modulo Carlson packing, we have this picture. We have a scale R, we have a hyperplane that basically bisects the ball or the cube, and the picture is this: above that hyperplane, but inside the ball or cube, that's clean, there's no boundary there. There's boundary here. In fact, a lot of boundary here. So much boundary that if this is at scale R, then the holes here can be at most epsilon R in diameter. In other words, each point here is within epsilon R of a point of the boundary. Now, there can also be some other boundary down here, but that doesn't bother us. And in fact, using stuff that David and Sims had already done, it's easy to see that if this holds modulo packing, so David Sims ideas, is that if this holds modulo packing, then this gives uniform rectifiability. In the elliptic case. Okay, but this is why the parabolic case is fundamentally more difficult, is that these kind of Carlson set packing conditions do not imply uniform rectifiability in the parabolic world. Okay? Okay? It's just false. They're counterexamples. Okay? So when we got to here, we were done. In the elliptic case, in the harmonic case, in the parabolic case, we're just getting started. And in these last, 5 minutes, I will tell you. I will tell you what needs to be done. So what do we do with that? All right. So what we're going to do is to prove corona approximation in terms of R-lip graphs. Okay? Corona approximation means this. You have your boundary is a space of homogeneous type. So it has a system of dyadic cubes. And a corona approximation means that the dyadic cubes can first of all be partitioned into two sets, a bad collection and a good collection. The bad collection packs. They have Carlson packing condition. The good ones are further subdivided into stopping time trees, such that on each stopping time tree, you have some kind of uniform good property throughout the tree. And in this case, that means approximability by R-lip graphs within the tree. Okay? All right. Guy knows what that means because he and Stephen invented this, but some of you also know what that means. If not, I'm sorry, it's a little complex, but okay. So the goal is then to prove this. So what are we going to do? So we've got this. We start with the WHSA. All right. And then we construct the trees. Following the ideas of Garnett's, what has now come to be called the epsilon approximability argument. Applied to grad U to get trees, which we'll note by S. I know S doesn't stand, tree doesn't start with an S. S stands for stopping time, on which throughout a sawtooth associated to the cubes in this tree, the oscillation of grad U is small. Okay? Which means that for the WHSA planes associated to these guys, those WHSA planes are going to have normals that are approximately the same, so that those WHSA planes, the WHSA planes are approximately parallel. We can even take them to be parallel if we like. Okay? Which lets us then follow a construction of David Sims again to construct a parabolic Lipschitz graph. Again, this is just lip 1, 1/2 for now. Let's call it sigma S associated to S. All right? So we need two things. We need that these be R-lip. We need this graph to be R-lip. And the second thing is that we need to be able to pack the maximal cubes of the S's, which is the remaining requirements of the corona approximation. All right? So for one, we get this by we push the weak infinity property onto sigma s. So once you know that the caloric measure for sigma s is A infinity, you invoke theorem 1. So that says sigma s is actually R lib. Okay, and in this packing, what you do, and I'm basically out of time, so maybe I'll just say it. To pack the maximal cubes, you need to think about what would it mean when this stopping time argument stopped. It means there's going to be a jump in grad u, which means that the non-tangential maximum of grad u in sigma s is going to be bounded from below as long as sigma s is catching one of the the domain above sigma s is catching one of the points where the grad u jumped. All right, and then you invoke Russell-Brown's lip 1/1/2 s less than n estimates, square function, or then n less than s, non-tangential max less than square function, on a cube where we know, or on a graph where we know that the caloric measure is A infinity, and then we use the Lewis and Eastrom result again to kind of glue things together and get a packing condition. All right. There's something I've glossed over, which is how do we actually know that the region above sigma s captures a point where we have the jump in grad u. And that takes some doing, and it doesn't always happen, but it happens a lot, enough that you can make things work. So thank you for your attention. I'll quit here.
Yeah, thanks for the... Yes. Yeah, it works. But thanks for the nice talk, the nice words at the beginning. Just to say that maybe I'll have more words, but maybe not now. Maybe we have best dinner, something like this. Okay. It's just a question for the time being.
Okay.
Just to make you believe that I follow up to the end. Grad u is a vector.
Yes. Yes.
Okay. So what's the oscillation of grad u? Because you have direction and...
Yeah. What I mean is, yeah. I just mean, we look at grad u of ys minus grad u of xt as y and s and xt range over certain places, basically Whitney regions relative to a cube q. Okay? And then, and I'm calling, this is what I'm referring to as the oscillation. Okay? And so when this is small, we get to play this game of building the graph. And when this gets big, when we get a jump somehow, that's when we get this. We can bound the cubes where that happened, at least a lot of the time.
So small is direction and size comparable. Okay.
Yeah.
Okay.
Yes.
Okay.
Yes. Yeah. 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 This is what we. Yeah. No, that's right. I glossed over that, but yeah, there's this. Remember, there's this. There's this fact, and you could say even more than that. Okay, we don't have the Caferli-Salsa thing, right? A directional thing, but we can say that that at least there's some points in the Whitney region relative to a cube Q where this is non-degenerate, in fact, like 1. Okay, but then if that happens at some good point and then the oscillation is small, then it's happening throughout the Whitney region. Yeah. Yeah, that's a good point. But yeah, we're covered on that. It comes from this and the fact that actually even more the weekend friendly property lets you say that you've got something like this, at least somewhere.
Any other questions? If not, then I have one. Have you guys looked at the risk transforms yet?
The parabolic ones? Oh, God forbid. I said, God forbid. Actually, no, that's a good question.
Well, I
That's
mean,
it's a really good
actually,
question.
in the context that we did with you and Chema, I mean, I'm not asking for the NTV stuff, right? I'm saying, like let's just impose the one-sided NT like we did, and whether we can get the balls outside.
Actually, no, you're right. You're absolutely right. In the parabolic case,
I think
in the
that
parabolic
should
case,
be
in the parabolic case, even that seems to be hard because in the parabolic case, even in the graph case, we don't know. Even for a lip 1/1/2 graph, assume the Riesz transforms are bounded.
Yeah, can you
Does that mean it's an R-lip graph? We do not know. We don't.
But I think that at least in that context, I mean, there should be a pass. It's not. I'm not suggesting the NTV business. I'm suggesting just
Yeah, I mean that would be the first thing to try, but even that I think is a challenge. I think it's a good problem because it seems to be a real challenge. It's not an obvious thing at all. Yeah.
There's even other difficulties, right? If you assume the graph has small constant, it seems pretty possible to use some recent work of, or well, not so recent, I guess some work of Tulsa. But if the graph has large constant, you can't do the stuff like Guy did, where you find like a piece, like a big piece of a nicer graph, right? So that kind of build-up scheme doesn't work.
Anyway, we're probably.
Yeah, well, you make a good point. Maybe that's worth revisiting.
I think it's a most. We're not
it
ameliorating into bigger pieces or something like this. This is just like securing that you have some non-vanishing, hence you have an empty ball inside or outside.
Yeah, because I mean you're right because we somehow were able to tie it to a harmonic measure.
I feel like you are doing this non-vanishing of the gradient sort of intuitively, and you should be able to
Yeah, because we tied it to the harmonic measure, so maybe one can tie it to the caloric measure, and maybe that's the way to approach it.
Exactly.
Yeah.
And that doesn't require.
That's worth looking at. Yeah. I agree. Yeah.
Let's thank the speaker again then.